is about free body diagram. So there is a man in an elevator, and the elevator is moving up. And we just have to draw the free body diagram. Easy question, but however, there are people who get it wrong. You have to understand the free body diagram is on the man, not on the elevator or anything else. So if we take the man and we have to look at what are the forces acting on the man. Right, so this is the guy. I take him out, so I'll put a dot for that guy and think of what he is interacting with, right? So he has a mass, so gravitational force, that means Earth will interact with that guy. So the force from the Earth on the man will be pulling him down. So that's a gravitational force coming from the Earth. No other forces from the Earth except that force. And the man is standing on the elevator floor. So the elevator floor is going to interact with the man. So the force of the elevator floor on the man will be pushing the man up. That's the normal force. These are the only two forces acting on the man. So someone will say, what about the tension force? Well, the rope or the cable that is connected to the elevator, it is not connected to the man. The man, the rope is not tied to the man. It is only tied to the elevator. So it is not interacting. The man is not interacting with the rope. So that tension force of the cable or the rope is not acting on the man. Only these two forces. So that will make the correct answer to be C. A. Yeah. What is wrong with the C? C, it is not the N, but it's the tension. So that is wrong. Good. So let's go to the next question. If we see an object moving with a constant speed and direction, we know that it must have, this is the Newton's first law, right, which says if an object is at rest, it will continue to be at rest, or if it is moving with a constant velocity or at rest, zero velocity also can be considered as one velocity, and if it is constantly at rest, it's also constant velocity, unless a non-zero net force acting on it. So according to that, now we see an object having a constant speed and direction. That means it has a constant velocity. So we know there are many things about this object. We can say its acceleration is zero because it has constant velocity. That means acceleration is zero. So if the acceleration is zero from the Newton's second law, we know the net force is also zero. So if you look at this statement, and we can eliminate what is not true. The force pushing it along, you don't have to. It says must, right? So there may be more than one force, then the net force may be zero. But if you say there is a force pushing it along, then it will introduce an acceleration. If there is a one force only, there will be acceleration. Acceleration means velocity will change. It will not be a constant velocity. That means this is wrong. No forces acting on it. Okay, so it is not strictly true. Of course, when there are no forces acting on it, the velocity will be constant, acceleration will be zero. But when you say must have, we can have many forces acting on it, but with the net force equal to zero. So that's why this is not strictly correct, because he says must. We can have a situation where there are more than one force acting on it, and the net force is equal to zero. Therefore, it can have a constant velocity. So that's why this is wrong. Okay. It has an acceleration? No. Constant velocity means acceleration is zero. D. No, that is correct all the time. Okay. When there is no force, that's also mean net force is zero. There are more than one force, and the net force can be zero by cancelling each other. the net force can be 0. So that is correct all the time. No friction acting on it. I mean, there may be friction, there may not be friction. That's not a condition for it to have a constant velocity. So that is eliminated. Okay, question number 3. A constant force of 160 Newton is applied to a 86 kilogram crate on a rough level surface at an angle of theta equals to 24 degrees above the horizontal. So we have a picture. Okay, even if you are lazy to read the question, we can get the whole thing from the picture. That is nice. So we have a force applied, not a horizontal force, it is making an angle of theta with the horizon. Okay, and the angle is given, I believe. Yep. And the force value is given, and the mass of the crate is given, and it's a rough level surface. That means there is a friction force acting in the opposite direction to its motion. Now we have to answer this question, which of the following statement is the correct statement? So it is about getting an expression for the normal force, right? So we can apply the Newton's second law in the y direction, because knowing that the n is in the y direction, so naturally we'll go for the y direction. So we'll have an equation with normal force in it. So the net force in the y direction, we mean the component of all the forces, right? The net. So we have to include all the forces. So let me start with the normal force. Normal force in the positive y direction, so plus n. And no, let's go one by one. Let me go to the applied force, okay? Minus, well, let's go one by one so we don't miss anything. So I finished with the normal force, now we with the applied force. So its y component will be, it will be upright, it is positive. So it is plus f sine theta. You know why it is sine? Because theta is the angle making with the x-axis, so the y component will be and sine, f sine theta plus. And that is done, this is done. The mg, it is negative. And that's very clear. And f is entirely in the x-axis, right? So the component of f in the y direction will be 0. I'll just put 0 just to, this is coming from the friction force. It has no contribution in the y-axis. So we covered all 4 forces and its component along the y-axis. Mass multiplied by acceleration. Do we have an acceleration in the y direction? No, it is only moving horizontally. So its y is not changing at all. So that means it has 0 velocity in the y direction and constantly 0 velocity. That means acceleration is also 0 in the y direction. So this is getting this equation, n is equal to mg minus f sine theta. So we know, looking at this, because these are all positive and there is a negative subtraction. Oops, let me rewrite this. So this is positive, we are subtracting a positive value from mg. That means n is going to be less than mg. Hala, is good? Okay, right, so n is less than mg.
Yes, doctor.
All right, okay, good, thank you. So let's move on. So please ask me to stop or pause, or if you have a question, I will explain. Right, number 4. A block of mass m is pulled up a rough incline with a force of magnitude f, and in the direction as shown in the figure. As the block moves up the incline with an acceleration of magnitude a, the kinetic friction force Fk acts on the block. So again, we have a picture that's very nice. You don't expect to get a picture all the time, okay, image. So sometimes you have to draw the picture yourself. Right here, nice, we have a picture. As the block moves up the incline with an acceleration of magnitude a, kinetic friction force, even the the free body diagram or the force diagram is already there, covering all the forces acting on it, and even the direction of y and the x is chosen for you. Okay, always, yeah. X-axis is along the motion, right? Don't choose the x-axis like this, because here it is not proper to choose the x-axis like horizontal. It is proper to choose the x-axis along the incline. It is already chosen for you. So that's what you should do when motion is along an incline, right? So let me get this guy out. Now, this is not a numerical question, but to test whether you know how to apply the Newton's second law. So, he is even telling us, apply the Newton's second law in the x direction. So, you're being helped a lot. So, net force in the x direction is equal to mass multiplied by acceleration in the x direction. So, the net force, net mean you have to include all the forces. Let me start with one by one. Second law in the x direction. So this is the net force in the x direction. We have got 1, 2, 3, and 4 forces acting on it. So we'll start with the normal force. At sum of all the forces in the x direction, one by one. X is entirely in the y direction, so it has 0 component in the x direction. So I put 0 for the normal force. And this applied force F has a component of F sine 70. So please note that it is not cosine 70, because 70 is the angle it is making with the y-axis. So along the x-axis, it will be sine of the angle 70, which is the angle F making with the y-axis. And it is pointed upward along the y-axis, along the positive y-axis, so you put positive. mg. Next force is the gravitational force. Incline angle is 30 degrees. That will make this angle to be 30 degrees. We can prove it with a little bit of geometry. I will not go into that. Just remember, if the incline angle is 30, that will make this angle, that the angle mg makes with the y-axis. Of course, the negative y-axis will also be the same, 30 degrees. Now, the x component, therefore, will be mg sine of that angle 30. The same reason like for the applied force, mg is making an angle of 30 degrees with the y-axis, not with the x-axis. So that will make the x component to be sine of 30 instead of cosine of 30. And again, the direction will be in the negative direction for that, because the positive x-axis is up the incline. So, but mg is pointing downward along the x-axis. So it'll put a negative sign there. And finally, the friction force, it is pointing in the negative x-axis. So it will be minus Fk. And we finish with all the forces. The left-hand side is done. We go to the right-hand side. So mass multiplied by the acceleration. So this is the equation that result from applying the Newton's second law in the x direction. That corresponds to choice D. A block of mass m1 equal to 10 kilogram and another block of unknown mass m2 which is having a mass greater than m1, m2 is greater than m1. So this will make m2 to go up, and m1 is heavier, so it will go down. Over a massless frictionless pulley, if the tension in the spring is 75 newtons, so the tension is given to us, and mass m1 is given to us, the question is to find the acceleration. Right. So if you go to m1, because the mass of m1 is given, whereas the mass of m2 is not given. So the wise thing to just go with the one that is more things are given. So we will be able to reduce the number of unknowns if I apply the Newton's second law on m1. So for m1, I'm going to apply the Newton's second law. Net force is equal to mass into acceleration in the y direction, let's say, vertical direction. So m1, what are the forces acting on m1? The tension will be pulling it up, and the gravitational force m1g will be pulling it down. Only those two forces. We don't have any other forces, not touching anything, so there are no contact forces. Right. The net force in the y direction, T is positive, and M1G is negative. So please remember to put the correct subscript, because if you just put M, then you're going to get confused whether that is M1 and M2. We don't know. So we better put that correctly. And the tension is, of course, the same everywhere on the string, if it is a massless frictionless pulley. But I am not worried about M2 now. I am applying the equation on M1. These are the only two forces. So I covered the left-hand side is equal to M will be M1, and acceleration will be an unknown, right? We are asked to find the acceleration. Tension is given, mass 1 is given, G we know 9.8, M1 is again given. The only unknown in this equation is A. So all you have to do is to substitute. T is 75 minus M1 is 10 multiplied by 9.8 is equal to M1 again, 10 into A. So you see that this you can easily solve, right? You don't even need to do the equation solving. If you want, you can. Okay, it's fine. So let me bring my calculator. Right. So you just write the equation in there. 75 minus, if you like, you can do it in your mind. 10 into 9.8 is 98, right? You can do that too. Okay, if you feel confident about that, you just go ahead. Why waste the time? Equals, so alpha calc, 10 into A. 10 multiplied by A is what? A is, is the unknown. You're going to call it X. Let's solve it. Shift calc equals, okay, you get a negative value, right? Because A is a magnitude. A is its magnitude. You get A is its, we don't know whether it is, we could have done like already we know A is down, then we could have put the negative sign on it, then you'll get a value of positive value, because you are considering as a magnitude. But here we did not, we just put A, then it is giving the direction of A. We took the positive direction up. Since you are getting a negative value, its direction is down. That's correct. But he is asking for, maybe I should have mentioned what is the magnitude of the acceleration. But it doesn't matter. Okay. What is the answer we got? Did we get the correct answer? 2.3? Yeah. Okay. Minus 2.3. The minus tells you its direction is downward. Number 6. So now we come to chapter 5, work, right? So usually the question is, first, this one is an easy question. So it's depending on the definition of the work. For a constant force, the work done by that constant force F is given by this is the component of the force parallel to the displacement multiplied by the displacement. So this is the equation of the definition of the work done by a constant force. So now the displacement, the mover is moving in a certain direction. This is your delta x. So this person is moving it. So, and the force applied is this. So the force is like this, and it's making an angle of theta with the horizontal direction. So the theta is given to us 60 degrees. So that is perfectly clear. There is no confusion. And we know the F, 100 Newton, and we know the delta X. All you have to do is to substitute them and get the answer. I will not bother going through the calculation. Say, yeah, yes, you can see it. You can even do it with your mind. But cosine 60, it is positive, right? Why? See, this is the object that is being moved. Okay, and it is going like this. So this will be the displacement of the object. Okay, so the direction of the displacement is to the left, and you have the force that is applied like this. You can put it like that also, it doesn't matter. Okay, because it is acting on this, so you can say the direction of F is like that, and direction of delta X is like that. So the angle between F and delta X is this. So delta X and F, they are both in the same direction. Well, meaning the angle is less than 90 degrees. Okay, when theta is less than 90 degrees, cosine of theta is positive. If the theta is greater than 90 degrees, cosine of that theta will be negative. So it is like, if suppose something is going towards you with a certain speed and you apply the force in the opposite direction, so the displacement will be still, it will come this way. Although you are applying the force in the opposite direction, displacement will be like this, and the force will be the right, and the angle will be 180, right? Cosine 180 is -1. So theta, when it is between 0 and 90, it is positive. At theta equal to 90, it will be 0. Then from 90 to 180, it will be minus. Okay. So question number 7. You throw a baseball straight up. Compare the sign of the work done by gravity while the ball goes up with the sign of the work done by gravity while it goes down. So, when you go up, you're throwing something, it is going up. When it is going up, delta X is up, and the force of the gravity force, right? We are looking at the work done by the gravity force. Gravity force is always down. So on the way up, the work done by the gravity force, you are not looking at the work done by anything else, but the gravity force. Gravity force is downward, displacement is upward, they are in the opposite direction, angle is 180, cosine 180 is -1. So the work done on the way up will be negative. The work done by the gravity force when the ball is going up will be negative. And when it is coming down, it's the other way around. Going down, the gravity force is, again, it is down, it is not changing, but the displacement is also down. So the angle between displacement and the gravity force is the same. That means direction is the same. That means angle is 0. Cosine 0 is +1. So because they are in the same direction, the work done will be positive. So that's why the B is the correct answer. All the other answers are wrong somehow. The work is negative on the way up, positive on the way down. Work done by you. So we can have variation of this question. Okay, so it's like, suppose somebody is taking a ball and moving it up, and you can ask, what is the work done by you? mean the force is the normal force from your hand on the ball. So in that case, when you go moving it up, the work done by you, not by gravity, is positive. When you bring it down, your force is up, displacement will be down, then it is negative. So you can have a variation of the same question, right? Here the question is about what is the sign of the work done by gravity. Suppose I can change it to what is the work done by, suppose they are not throwing here, right? The baseball is throwing up, there is no force from the hand. But instead I can change the question to read like you're moving a ball, keeping your hand and bringing it up. What is the work done by you or the force by you? That will be positive on the way up. On the way down, it will be negative, the work done by you, not by the gravitational force. Opposite, yes. A mechanic pushes a 2000 kilogram, right? Yeah, 2000 kilogram car from rest to a speed of 2.5 meter per second. During this time, the car moves 20 meters, neglecting friction between the car and road. Find the work done by the mechanic, right? So this is the work kinetic energy theorem. So do you remember it? Ahmed, right? No, work done, net work is equal to delta K, work kinetic energy theorem, right? So we know the definition of work by a constant force, and we know what is kinetic energy, the definition of kinetic energy. Half. No, if you have a mass m and a velocity v of a one object, its kinetic energy will be half m into speed square, mass into speed square. Right? When you have two balls, that's a different. But if I ask you what is the kinetic energy of something, an object having a mass m and a speed v, the answer is half m into speed squared, right? Half mass. So we are talking about a car which has an initial velocity of 0 and final velocity of 2.5 meter per second squared, and the mass of the car is this, and it is moved this much of distance, say along the x-axis. What is the work done? So, we don't have the forces to calculate the work done by the force. Okay, the definition of the work done is f cosine theta delta x, but we don't know the forces. But we know there is something being pushed, and we know its initial velocity, initial speed, and the final speed, and we know its mass as well. So then you remember that is we can get the change in the kinetic energy of this guy. So I can put it in there. This whole thing is given to us, and the work done by the force, we can say it is equal to the change in the kinetic energy. So all I do is now just calculate the change in the kinetic energy, and that will give me the work done by the mechanic. Okay, here we are neglecting friction. So there are no other forces. The net work will be simply the work done by the mechanic, okay, because there are no other forces. Well, there will be vertical forces that they will not do work. So the only force that do work will be the mechanics push, right? Whatever. So we all have to do is to find the change in the kinetic energy. That will be the work done. Half into 2000, that is the mass of the car, multiplied by final speed is 2.5 meter per second. Initial speed is 0. And when you do that, you should get this answer. So, right, let's go to the next question. A 3 kilogram box hitting on a smooth table at rest at the position x equal to 2 meter was pushed by a horizontal force 8 Newton in the positive y direction. What is the speed of the box as it passes 5 meters? Okay, so here again, we going to apply the work kinetic energy theorem. So we have a box which is at x equal to 2 meter position, and it is pushed by a certain force, and it moves and comes to the position 5 meters, and when is the x equal to 2 meter initially, it is at rest. So velocity here, initial 0, and being pushed with a certain constant force, and through a distance 2 meters to 5 meters, that means 3 meters being pushed, and when it comes to the x equal to 5 meter position, we don't know what the speed. The question is to find that speed. That's what you're asked to find. So, right. Okay. In the same equation, the network is equal to change in the kinetic energy. The force is given to us. So the work done by that force will be smooth table, right? So that will, there will be no other forces. Yes. So F is 8 multiplied by the horizontal component. It is pushed horizontally, right? It is sitting on a table, pushed by a horizontal force. So that means theta equal to 0. The angle it makes with the displacement is 0. So cosine 0 is 1. So simply multiply by the distance, which is 5 minus 3 equals change in the kinetic energy half. M is equal to 3 kilogram, and final speed is the unknown. Initial speed is 0. Is it 0? Yeah, at rest. So only unknown in this equation is final speed. So again, to save time, we can just, it's not a difficult question. You can, just do it the normal way. 8 multiplied by 5 minus 3 is how much? This is 2. 8 into 2 is 16, right? 16 is equal. 5 minus 3 is 2, right? 5 minus 2. Oh, 5 minus 2. Oh, that is 3. God, I'm making so many mistakes, right? And I'm being recorded. Okay, right. 8 multiplied by 5 minus 2 is 8 into 3 equal to half into 3, and this is 0, so Vf squared. Now 3 cancel with 3. 2, when it come here, it becomes 16. 16 is equal to Vf squared. You know what it gives? Vf is equal to 4. You don't even need a calculator for this. Okay. Question number 10. This question I repeat so many times, I will just skip that. Number 11. As shown in the figure, a box of mass 15 kilogram is released from rest at position A. At the top of a 30 degrees frictionless incline, the box slide 4.7 meter down the incline before it encounters at position B a spring and compresses it an amount of 0.180 meter to point C. So this value is given to us. So here it starts with the 0 velocity, and it comes down because of the gravitational pull. It hits the spring that is here. Okay, the box is initially here. It hit it and compresses it, and there is a compression of this much. And then again, at this point, the velocity becomes 0. So initial is when the block is here, and the final is when the block compressed the spring to the maximum. Then of course it will spring back, it will recoil. I mean, the spring will push it, but we freeze the time there. Okay, so 0 here. Finally also the block is at 0. Where is the energy go because it has gained energy, right? By the time it comes here, it will have some kinetic energy. That kinetic energy is lost to the spring. So, but to do it a proper way, because we have a nice equation, the most general equation, the conservation of energy principle, work done by any external force plus work done by non-conservative forces is equal to change in the kinetic energy plus change in the potential energy, all kind of potential energy. So we have a gravitational change potential energy and spring force is also there. So this is how I would write most generally. Then we say our system consists of the box, the spring, the incline, and the earth. And for that system, we don't have any external forces. So this is 0. Okay, no one is pushing it or pulling it, right? It is the forces, both the spring force and the gravitational force is part of the system. So there are no external forces. And also we say it is a frictionless incline. So this guy is also 0. So we have conservation of energy, right? So there are no non-conservative forces and there is no external force, isolated system. So this is 0. Change in the kinetic energy is also 0 because initial kinetic energy is 0, final kinetic energy is also 0. 0 minus 0 is 0. So the kinetic energy 0 minus 0, that becomes 0. Plus change in the potential energy, of course there is a gravitational potential energy change, the block is going down, so that will be mg, and I need to know this vertical height, right? Let me call it h. So if h stands for the magnitude of the height that is dropping, so I will put minus h. H is for the magnitude of that height, the block is going down, and then I put a negative sign to remind me, I better make it negative, right? If you know the h, is that the question? No, it is given to us. Well, indirectly, not directly, I will come to that. And the spring, change in the spring potential energy will be, it is half plus k. How much is spring is changed finally and initially. Initially, the spring is relaxed, okay? Initially, the spring is relaxed. So initial compression is 0. Final compression is xc, which is given to us, 0.18. The only little bit of challenge is getting the h right. Because from here to here, it is how much? 4.7. But from here to here, there is another 0.18. So the h will be this distance, which is 4.7 plus 0.18 multiplied by sine of this angle. So h, if this has a symbol, right, d, so it will be d plus x sine theta. Okay, the magnitude, d plus x sine theta. I need some space to 4.7 plus 0.18 d plus x. H will be that much. So here, I mean, you can, we can have a kind of a shorthand shortcut. Sine, because sine theta is equal to opposite divided by hypotenuse. That will make the opposite side to be equal to hypotenuse multiplied by sine theta. So minus mgh is equal to half k x final square. So if you want a shortcut, if you can identify it in the same problem, you can put it this way. This tells you that change in the gravitational potential energy is transferred to the spring potential energy, completely transferred to the spring potential energy. So we know what H is, but we better calculate it correctly. H is equal to d plus x sine theta, the magnitude of H. We know everything except the spring constant, so I can calculate that. H is, you want me to do that? Okay, fine, let's do it. So let me bring the calculator in. So let me bring it here. Let me clear the thing. So I will write this equation into my calculator. So M is, help me, what is M? 15 kilogram. Okay. Multiplied by G is 9.8. Multiply by, I'll put in the bracket because we are going to have the D plus X. D is how much? 4.7 plus X is 0.18. Close it. This is the D plus X. Multiply by sine 30. Is it 30? Okay. Right. This is on the left-hand side. So I will say alpha equals, so I got this part done, half. So I can use this for half, 1, or I can put 0.5, doesn't matter, and bring it up. Multiply by k, k is our unknown, alpha x. Multiply by, this is given, right? How much is 0.18? Square it. That's it. So you do it once, so you don't make a mistake. Then if you are confident, you can just go shift calc, enter, and it'll give the answer, 22,140. Why don't we see the 4 and 0? Because it has been rounded to 3 significant figures. So the last two digits are dropped, so it becomes just placeholders as 0 and 0. So it becomes 22,100. Okay. Right. Let's move on now. Next question. Question 12. This is a question on power. So an electric motor of a model train, it starts from initial velocity of 0 and reach a speed of this, so this is the final velocity, in this amount of time. The mass of the train is given. The question is, what's the average power? So if I use the symbol P for the power, it is the work done divided by the time. For the work done, we can use the change in the kinetic energy. So that will be because we have the initial speed and the final speed. From that, we can get the change in the kinetic energy. And the time duration is also given to us. So we can get the power simply by dividing the change in the kinetic energy, which I can write it as half m, final speed squared minus initial speed squared, divided by the time. So it's now a matter of substitution. So let me collect all the values. M is 0.680 and final speed is 0.800, square it, minus initial speed is 0, square it, divide by the time taken, 0.0220. So this gives the network, and it's equal to the change in the kinetic energy divided by the time taken will give us the average power. If you do the calculation, Just make sure you are getting this as 9.89 watt. This is a easy question in the sense, just the definition question. We have three objects having different momentum. We ask to find the total momentum of the system of three objects. So you just M1, V1I, not V1I, M1, V1 plus M2, V2, but just remember they are all vectors and the velocities are given in vector notation. So you just substitute because answers are also in vector notation. So you don't have to go in the x direction, the y direction separately. You just do a vector addition for the total momentum. So M1 is 0.5 multiplied by 8 and 0 because we have two-dimensional problem, x and y, 8 and 0. And plus M2 is 0.5 and here you can see V2, we can write it as minus 2 and 0. Okay, it's also 0.5. Yeah, third one is also 0.5. All of them same mass. And this one is 0. There is no x component and plus 8. I don't need to put the plus sign. It will kind of confuse. So let me take it out. Yeah, only if it is negative, better make sure you put the negative sign, but now. Right, this is just quickly do it. So 0.5 into 8, 0.5 mean half, right? Half multiply 8 will be 4. Plus half again, this will be minus 1 and 0. And half again, that will be 0 and 4. Now add them all. You know how to add vectors. You only add the x's. 4 minus 1 will be 3. 3 plus 0 will be 3. And the y is 0 plus 0 plus 4 will be 4. So the answer is A. Now suppose if I ask you what is the magnitude of the total momentum, what would you do? This squared plus this squared and take the square root, that will be 5, right? So that can also, variation of the question. Instead of, I'll go one more step. So you will first find in the vector form as the x and y component. After that, if the question is find the magnitude of the total momentum of the two objects, then you will say 5 kilogram meter per second. Right, that I will not waste my time there. Number 15. Right. This is also a nice application statement question. Okay. So why doesn't it break on a soft, spongy or grass? Because it will take more time to come to zero speed. On a concrete floor, it will come to zero immediately, like very few fraction of a second. So that will make the impact force smaller when it is on a grass because the time is greater, because the force is equal to the equation that you using is this. The average force is equal to change in the momentum divided by the time. Change in the momentum is the same in both cases, whether it is grass or road, but the time is greater in the case of the grass. So the force will be smaller. Number 16. In an isolated system with two moving objects, when a collision occurs between the object, you know that, right? If it is isolated, momentum is conserved. Can have collision, doesn't matter. All these are internal forces, right? But even when it is not isolated, when we in a normal collision, it is not isolated. There are external forces, but we say during the collision, it is a very short period of time. I can ignore all the external forces because compared to the internal forces that act during the collision, those external forces are quite small compared to the internal forces. And also, its a duration is very small, so we can safely ignore them. That's why we say in general, in any collision, momentum is conserved. Okay. It doesn't have to be elastic collision. Whatever the collision, the momentum is conserved. Please remember that. But only thing that distinguishes between elastic and inelastic collision is the kinetic energy. Kinetic energy conserved mean it is elastic collision. Otherwise, it is inelastic. So you know the answer to this one as well. So I can ignore that. Go to question number 18. A block of mass, 200 gram, m1, moving on a frictionless surface with a velocity of 3 centimeter per second, makes a head-on. Head-on mean one-dimensional. After collision, they all move in the same line. That is the meaning of head-on. Head-on mean the collision is one-dimensional, okay? They are not glancing. They don't go in different direction. It will be in the same line. It may recoil, move in the opposite direction, but in the same line. With a block of mass m2 equal to 120 gram moving with the velocity of that one, after collision, m1 stops. You understand what do you mean by stops? Stops mean V1F is equal to 0, right? Is m1. Okay. m1 comes to a stop. That means final velocity of m1 is 0. So we have here, the equation is this: net momentum, total momentum before collision is equal to total momentum after collision. We can apply to any collision. Total momentum before is m1 v1I. They are vector equation. That is what you have to keep in mind all the time. This is the total momentum before. This is the total momentum after. Okay. Right. Total momentum before, so we can substitute values. So 200. See here, the beauty is, although we'll think, okay, there are two unknowns, V1F and V2F, but he has given the V1F. He has given all the initial velocities, he given all the masses, and he is also given the final velocity. That will make only one unknown in this equation, V2F only. So V1F is given. Okay, that is one thing you have to be very careful. You should identify what is M1, what is 2. So M1 he is saying 200. So that will make, it's already been helped a lot, right? V1I is given. And M2 is given. V2I is also given with the sign, okay, with the sign. So it's being helped a lot. V1I is 3. M2 is 120. About the unit, it is in gram and the velocity is centimeter per second. Do I have to worry about converting? No. M is occurring in both sides of the equation. Everything is in gram, so no problem. And velocity is given in centimeter per second. Keep it that way. And you need the answers also in centimeter per second. There is no need to convert anything. 200 multiplied by 3, 120 V2I is -1 equal to M1 again, which is 200. And V1F is 0. And plus M2 is 120. And that is the unknown. Call it X. So, X is actually V2F. So you just take your calculator, you use the calculator when you know how to use it. So you will not make a mistake, hopefully. So, just you can save time, moving things around, doing the algebra. You can go like, even if you can do it manually while you are using the calculator, that is also good. 203 is 600. Minus, I'll put the minus straight away because I can see there's a -1 multiplier, so 20, and equal sign. And this is 0. You don't even bother to write it. 120 multiplied by X. Okay, that's it. You don't have to worry about anything. Let the calculator do the job for you. Shift calc. This is not the answer. That is from our previous calculation. 4. Plus 4. When you don't see a sign mean, it is plus, right? So plus 4. Right. Number 19. It's also collision problem, but two-dimensional, right? Should it bother you? No, right? So it is the same equation. You finally will get this M1 V1I plus M2 V2I equal to M1 V1F plus M2 V2F. But now perfectly inelastic. M1 and M2 has the same velocity. So you don't have to put two terms here. You will just write M1 plus M2 V. Just call it V, VF. Okay. Right. So perfectly inelastic collision, they both going to have the same final velocity. There is no need to call it V1F and V2F. We just call it VF. Matter of substitution. So M1 is 1200 and V1I, but you have to better bring the vector thing, okay, the angle bracket. So tell me, east, we are taking the east as the positive x-axis and 0, nothing in the north, plus M2 is how much? 600, and component will be the 0, and make sure you put the 0 first for the x component, and the y component is 30 plus equal to M1 plus M2, do the calculation, 1200 into 600 is 1800, and our unknown, call it x, and solve for x. Well, this is, you don't need the calculator in the solving mode or anything, you can just do it. 1200, but somebody help me please. 1200 into 15? 1800? 18,000 and 0 plus this one 600, 0, 600, 1800, also 1800, 18,000, okay, equal to 1800 x, and 18, let's do this now. So 18,000 and 18,000, right? Equal to 1800. Now you know you don't need a calculator now, because 18,000 divided by 1800 will be 10. So that will give me V final is equal to 10 and 10, right? B, okay. Usually we do this to make the calculation easy. Right. So this is something that when you, this is the rotation chapter. When something is rotating about a fixed point, every point in the rigid body have the same angular velocity. So that's this question is about. So that's why same angular velocity means it covers the same angle, equal angle in equal time interval. So it's another way of saying if a wheel turns with constant, oh no, it's not about, I just assume. What is the question say? If something is moving the constant angular speed, that means it's covering same angle in a same interval of time, right? Like if something is going with a constant velocity, normal linear velocity, that means it's covering same amount of distance in a given time interval. So here instead of distance, it is angles. All the rest are wrong. Each point on the moves with constant velocity, no, constant angular velocity is correct. But constant velocity, that is not correct. They will have different tangential speeds. Question 21. If a wheel turning at a constant rate completes 6.43 revolution in 40.4 seconds, its angular speed. So that is, also an easy question. Just on the definition of what is angular speed, omega is delta theta over delta t, right? So it's the average angular speed, but since it's a constant rate, so it means it is also the angular speed at any point in time. The average angular speed will become this angular speed at instantaneous angular speed as well. So you just have to do this, but the answers are in radian per second So that's what we have to worry about, conversion of unit. This is not in radian, but in revolution. So you have to convert the revolution to radian, and delta t is already in second, so that is fine. So only the revolution has to be converted to radian. Yeah, you know, one revolution is 2 pi radian. That's it. Okay. Sometime, you know, you may get the, instead of second, you might give in minute. Then you have to convert the minute to second. So you know how to do that. So this is slightly easier question. I will not bother to calculate it. You know, so let me, you know how to do that. Okay. So question number 22. You are riding a bicycle due west. Seeing a vehicle in front, you apply the brakes to slow down your bicycle, still moving due west. What is the direction of the angular velocity of the bicycle wheel as it slows down? These are unnecessary things, okay, because angular velocity direction does not depend on whether you're slowing or, okay, it only matters if the question is about acceleration, right? And you know how to do this, right? If you are moving in a certain direction, left side is the direction of the angular velocity. So if you are going west, the left of west is south. Okay, you should be able to do it. You know, I can give the same exact question, but I can make the guy going in the north or do crazy things. Okay, so you shouldn't, you know, this should be easy by now. Okay, but when it is angular acceleration, suppose the question is changed to acceleration, then you have to pay attention to whether it is slowing down, whether it is increasing the speed or speeding up, or whether it is constant. Now, three things, right? Whether it is speeding up or whether it is slowing down, that is two. What if you're going with this constant velocity? Acceleration is zero. So when acceleration is zero, can you talk about a direction for zero acceleration? So I should have an answer which says none of the above, or no direction, or something. Okay, so something like that. Number 23, a bicyclist, whatever, starting at rest produces a constant angular acceleration of 1.20 radian per second squared. Then the wheels reach angular speed of 29 radian per second. How many radians have the wheel turn through that time? Okay, so here we have angular acceleration. So the kinematics now, this is alpha, and reach angular speed of rest. So starting with the initial angular speed of 0, and you reach the final angular speed of this velocity. It has a direction, that's very careful, but here probably doesn't matter, everything is in the same direction. How many radians? That means he is asking for delta theta, right? It's like chapter 2 questions, right? So you can say we have to worry about delta theta, that we don't know. In fact, that is the question. Then do we know the omega 0? Yes, 0. Do I know the final velocity? Yes, 129.2 radian per second. And do I know the angular acceleration? Yes. What is left now? The time. Do I know the time? No. Right. Okay, no problem. We have three things given, only two unknowns. So I can pick the correct equation to answer this question immediately without going through two steps in one step. The question is to find the time. I'm not interested in finding the delta theta. I don't say, okay, let me put it back in. It's a question mark, but I'm not interested in this. I'm only interested in the time. So that means I have to go and pick the equation which doesn't have delta theta in it, which is the equation number 2 in my, which is omega is equal to omega 0 plus alpha t. Simple equation. So substitute. So you can say t. You can do a little bit of algebra. So I can do that too, right? Little bit of algebra here, moving things around. If you don't like algebra, you can just use the calculator and do it, okay? Right. Omega is 29 minus 0 divided by alpha 1.2. Please check it for me. Do I get 350? No. What did I do wrong? 29.
2 multiplied by acceleration.
What did I do wrong? Bicyclist angular acceleration of that, we reach an angular speed of 29. No. Oh, what the time is question is not the time. The question is delta theta. Okay, this is correct. Of course, this is the time. Okay, is that the question? This is the danger of not reading. Okay,
You read it.
I know. I do this all the time. Okay. Yeah, I forgot the question is delta theta, not time. Right. Okay, no problem. So I don't have to waste doing all this because the question is to find the delta theta, right? So I took the wrong equation. I didn't do any incorrect solution. The solution is correct for the time, but the question is, I just wasted my time calculating it. So I have to directly go for the equation that doesn't have the time, which is delta theta. No, not that. Omega squared equal to omega 0 squared plus 2 alpha delta theta. Do you have the time in this equation? No. Let me take my calculator. So I'm doing things, wasting my time, so you don't waste the time. Okay. In the exam situation, this is why you have to be alert. You should have a good night's sleep. Omega squared. How much is that? 29. I remember it. Squared. Equals, right? Equals alpha, and omega naught is 0. I will not even bother to do that. 2 multiplied by alpha is 1.2 multiplied by delta theta is our unknown. That's it. Solve it. Please correct me if I make any mistake. All right. 350 radian. Okay, got it. Can move on now. Number 24. A bicycle has wheels that are 30 centimeter in radius. What is the angular speed of these wheels when they are moving at 4 meter per second? Right. What is this question? With the speed, it will be the speed of a point in the rim of the wheel. So we are connecting the tangential speed to the angular speed. So this is the equation. So the tangential speed is the speed of the bicycle, because the speed of the bicycle will be the same as speed of the point on the wheel at the rim, at the edge of the tire of the wheel. So Vt is 4 meter per second, substitute, and R is 30 centimeter, bring it to meters, so 0.30, and omega, just solve for omega. Omega is equal to 4 over 0.3. So that should be 13. Is that correct? I don't think so. Did I? It's correct? Okay. 4 over point. Do you get the 13? Okay. All right. I don't know why. I try to do it in my mind. 40 divided by 3. It is not exactly 13. Maybe some decimal. Yeah. Okay. Right. 13 point something. Yeah. Number 25. Suppose a 1500 kilogram car or 1500 kilogram car passes over a bump in the roadway. So it's like the car is describing a circular path, right? So at that instant, it is going in a circle with a radius of 20 meters. The radius of the circle is 20 meters. So it is describing a very big circle, vertical circle. What force does the road exert on the car as the car passes the highest point of the bump if the car travels at 10 meters per second? So it's again, a straightforward question. If you remember, the Newton's second law for circular motion, the net force in the radial direction is equal to mass multiplied by centripetal acceleration toward the center of the circle. So the forces are the normal force and let me get this thing out so I'll not confuse. I don't need the radius now. I'll show the forces. The forces are gravitational force down and the normal force up. And of course, there may be friction. Okay, there are going to be friction, but the friction is going to be horizontal, not vertical. So in the vertical direction, the only force, or in the radial direction, which is vertical here, in the radial direction, we have only the normal force and the gravitational force. We always take the positive direction to the center of the circle when you apply for uniform circular motion. Center of the circle is below, right? From the car, it is below. So I'll take that direction as the positive direction, the centripetal acceleration direction. The acceleration direction is downward. So mg is positive because mg is also downward. I'm taking the downward as the positive direction, minus n, that is the net force in the radial direction, equals mass multiplied by centripetal acceleration. And you know the centripetal acceleration has a formula, you should not forget that. V squared, the speed squared, divide by the radius, divide by the radius of the circle. Now let me look at this. I got the equation, the Newton's second law for this uniform circular motion. We know everything, right? Here, except what he's asking. What he's asking n. So just solve it. You can take up your calculator. Always do that. Once you know your equation is correct, you bring your calculator and then substitute. Clear everything now. M is equal to 1,500 multiplied by 9.8 minus x, right? That is the unknown, equal m again, 1,500 multiplied by, you can bring this guy in, so the fractions. V is much? 10 squared, right? Yeah, squared. Bring it down, and R is 10. Oh, sorry, 20. That's it. You just tell the calculator to work for you, and it'll give. Oh, sorry. Right. 7,200. That's correct, right? I was staring at the formula. What did I do wrong? Right. Number 26. We are in chapter 7, right? 8. Talk. That's the last chapter? No. Yeah, this is the last chapter. Yeah. A bar of length 1 meter. We have a picture. I'll just save some time. So we have the bar and the force is applied at point B. What is the torque about the point C? So these are important, okay? There are two things we need to worry about. What is he asking? He is asking the torque from this force. Which force? The force F applied at B. You should know where it is applied. And then you should also know, okay, you want the torque from that force about which point? About the point C. Torque from the force F about the point C. If you don't specify the rotation axis of the pointer through which you want the torque, you cannot answer the question, okay? That is very important, right? Now we got everything right. So you know the torque is given by RF sine theta. What is this F sine theta? Is the R multiplied by perpendicular component. F sine theta is the perpendicular component. Perpendicular to what? Perpendicular to R. And you should know what we mean by R. What is R? R is the distance or the vector that points from where you want the torque. Where do you want the torque? At C. To where the force is applied. Where the force is applied? At B. So you need CB. The arrow that you draw from C to B is your R. That's very important, okay? You remember that is a vector. The first point is where you want the torque. That is C. I want the torque at C. To where? To the point where the force is applied. That is B. So CB is our R. And angle is the angle between R and F. So it actually, so you have to bring tail to tail. So this will be the angle. Even if you take the other angle, it doesn't matter. You know why? Sine of this angle is the same as sine of 180 of minus alpha of that angle. In general, we have this identity in trigonometry. So it's very nice for us. So you don't have to worry too much about whether I took this angle or the other angle, because sine of that angle is the same as the sine of the other 180 minus theta. So we can be a bit loosey here, loose here. You don't have to worry too much. Right. So let me take it out of the way. I need some space. Okay, so we just substitute. So, you know, there is another equation I like to mention here is this one. Sometime you will have a question where we are not given the theta, but we are given the perpendicular distance to the point. Then you make use of this equation to calculate the torque. But here is not the case. We have the theta. So we just substitute torque will be equal to R is the distance CB. Do we know that? Yes, 25 centimeters. So in meters, it will be 0.25. And perpendicular component of, let me put this, perpendicular component of F will be F sine theta. So theta is the alpha here, which is 60. F is equal to 20 Newton. So 20 sine 60. So this is the magnitude of the torque. Okay, now you have to pause. Don't jump to the answer because you have to give the correct sign. It may be positive, may be negative. We don't know yet. We didn't look at it yet. Okay. So the answer, when you calculate it, you will get 4.3, but you pause. Okay, just don't. It may be negative, may be positive. How do I get the direction correctly? Yeah, if it is clockwise, if the force is trying to rotate it clockwise about the point that we are interested in, then you put negative sign. Clockwise is negative. If it's trying to rotate it counterclockwise, you put a positive sign. Now, how do I determine? It's very simple, right? Put your finger on the point, which point you want, C, right? Imagine I'm holding it at point C, and you're pulling it with the force F, and you can imagine, picture it, which direction will it rotate? It will try to rotate counterclockwise, right? So it is positive. Don't just look at this direction of the force. If you look at the direction of the force, it's down, right? You will try to put a negative sign. No, it's not like that. And you also have to remember, for the same force, suppose you are calculating about the point A. If you want to talk about the point A, it is clockwise, right? Suppose you calculate the torque. Suppose the question is, what is the torque about the point A? So put your finger at point A and see what happened when you pull with the force F. It will try to rotate clockwise. So you have to be conscious of these things. Number 27. This is straightforward question. I will not do it. M1 x1 plus M2 x2 plus M3 x3 divided by M1 plus M2 M3. You want me to do it? This is x center of mass, right? Each one has a coordinate. The coordinate M1 will be 1, 1. The coordinate M2 will be 2, x is 2, y, we'll assume it is 0 here, although it is a little bit above. Anyway, never mind, because we are not interested in the y center of mass, so I'll call it 0. And this one will be 6, 0, and this one will be 8, 0. So x1 is 1, x2 is 2, x3 is 6, x4 is 8. And M1, M2, M3, M4 all given. So the center of mass, x center of mass will be M1, x1 plus M2, x2 plus M3, x3 plus M4, x4 divided by M1 plus M2 plus M3 plus M4. Yeah, that's the definition of the center of mass or center of gravity. The center of gravity or the center of mass equation is this. Sigma my xi, the weighted coordinate of x, weighted by the mass, divided by total mass. Okay. If suppose I change the question to y center of mass, what happens now? It will be sigma mi yi divided by total mass. Okay, same thing, same thing. Number 28. Okay, this is a question that often repeated. So I can ask, instead of rotational equilibrium, what is the translational equilibrium equation? Then the answer is that, right? 29. All right. So here we have a beam. I don't need to draw it again. It is already there. So let me get it out. So see, this is the beam. There are many forces acting on it. A force tension acting here, and weight of the beam at the center, and at the support here, there's a normal force from that column which is supporting it upward. Only 3 forces. Question is to find, is it equilibrium? Okay, it is not moving up or down, it is not rotating, it is in equilibrium. We have complete equilibrium. The question is to find the normal force. So the trick is to use this rotational equilibrium equation. And again, when you talk about the torque, you need to mention which point I'm applying this. The torque has to be taken about a certain point, right? We call it x. So we have possible candidate. Maybe this point, let me call it A. Maybe this point, let me call it B. Maybe this point, the center, let me call it C. And maybe this point, let me call it D. It can be any point, even a point outside, let me call it E. Any point. It doesn't have to be on the object itself. If it is in equilibrium, the net torque equal to 0 should be satisfied no matter which point I take. Okay, so it is up to you to choose wisely, so you arrive at the equation as fast as possible. If you choose A, no problem, you will get a correct equation. If you take the point B also, you will get another different correct equation. But you are not going to waste your time. You want to arrive at the answer. There is a certain question, right? Arrive at the answer to that particular question as fast as possible. So the question is to find the normal force. This is the question. And tension is also an unknown. It is not given to us. The mass is given, so mg is given. Normal force is not given, tension force is not given, mg is given. So the way to choose the point is as follows. You pick a point, when you apply this equation, the resulting equation coming from that should only have n in it. T should not appear in it. If both n and t appears, you will end up with an equation with two unknowns. N is unknown, t is also unknown. Can I solve that equation when you have two unknowns? It's like asking you, let me say x plus y is equal to 3. And suppose someone asks you, find x and y, can you find x and y? There will be several answers, right? 1 plus 2, x equal to 1, y is equal to 2. Or maybe x equal to 0, y is equal to 3. So when you have an equation like this, you cannot solve for both x and y. Maybe you need another equation, but that's possible. But we want to answer this as quickly as possible. So we try to choose our point, the point x, such that the torque from t is not 0. The torque from t somehow we get a 0 value. Yeah. So what should be the point? B. Y, the torque from t at the point B is 0. What makes it 0? R is 0. Right? What is R? The distance from where you want the torque to where the force is applied. That means B to B. R is the arrow going from B to B. Can you draw a line from B to the point itself? That means R is equal to 0. So that's why we have to choose that point to be the point B. Now let's do it. Net torque means torque from all the forces. So how many forces we have? T. Okay, let me. Yeah. Torque from the tension T. Torque from the tension T. So I got the T. And then the torque from the mg. And the torque from the normal force. This is the net torque equal to 0. And I am going to choose the point B to apply it. And this guy is 0. And torque from mg. Let me take another color. Let me say green. So about the point B, right? So from B to where the force is applied, this will be the R for mg when I take the torque about the point B. So that will make it, how much is that? How do I know? D, right? D is equal to 1.25. That is half of L, right? I mean, the whole thing is phi. That means this will be 2.5 and this is 1.25. That will make this also 1.25. Okay, half of 2.5 is 1.25. So R for this guy will be 1.25 multiplied by mg. M is 30 multiplied by 9.8. Right, but you have to pause again. Let me put it correctly. Y, this is the magnitude, right? So tell me about the point B, mg will rotate the beam which direction, clockwise or counterclockwise? Put your finger at B. So I am fixing the point B and you are pulling by the force mg. Which direction will it turn? Clockwise, right? Clockwise. So negative. So I got this guy done. Now I'm coming to the normal force. Yeah. No, first, yeah, it doesn't matter, it doesn't matter where it is negative, that will make the entire equation negative, right? You don't think like that. You have a magnitude of the torque, which is 1.25 multiplied by 30 multiplied by 9.8. That is the magnitude of the torque. Then you decide whether to put a positive sign or negative sign for the entire thing. Okay, so, right. So now we go to the normal force. Do the same thing. I have got the red pen with me now. So the normal force is here, and I want the torque about the point B. So that will make the R will be this, my red line. That will be the R for the normal force now. Got it? That is very important. So we know R, and N we don't know. I'm going to call it N anyway, as with the symbol. That will be our unknown, the X. So R is equal to what? Plus 1.25. That will make it 7.25. Look at the R. You have to get that right, okay? R is not 2.5, not 1.25, not 5, all the way to B, right? I'm taking the talk about the point B. So normal force is here and B is here. So R will be this length. I put it in red. So R will be 2.5 plus or 5 minus 1.25, which is 7.
No.
5 minus 1.25 is how much? 2.5 plus 2.75? 3.75. Sorry. Oh, yeah, please. I mean, if you cannot do it in your head, you better use the calculator. Don't make any mistake. Or you can just write it in the thing like, okay, let me write it in. I don't have space here. I will come here. So I will, you can say it as 5 minus 1.25. So you can just put that, which is 3.25. But if you are lazy to do the calculation, you can put it like this. Yeah. 3.7. Oh, 7.5, not 2.5. Thank you. Multiply by what? Multiply by n. Now you decide the sign. Don't forget that step. So this is the magnitude. N is the magnitude. Okay, N is the magnitude of the normal force. Now the whole thing is now the magnitude of the torque from the force N. Now do the same thing. Put your finger at the point B and see you're fixing that point B. And if the only force is the normal force and you're pulling with that normal force, which direction would it rotate about the point B? Plus, counterclockwise, right? Now, Nuruddin, you're looking a bit puzzled. So this is, okay, let's say this is the point B. And normal force is like this. Which direction it is rotating? I'm fixing the point B counterclockwise. So it is. Okay. Please stop me, I want to follow this, otherwise equal to 0. Now go to your calculator, take your calculator. 0, you don't have to write the 0. There's a negative, so you have to start with the negative. It's safer to use this negative here. 1.25 multiplied by 30 multiplied by 9.8. Got that green part. Plus, start up left parenthesis, 5 minus 1.25, close the bracket, multiply by, you don't know what that is. What do? You put x. Alpha, right parenthesis will give you x. Alpha equal sign, put 0. Right, now solve for it. Shift calc, that is from the previous calculation, plus the equal button, 98. Do I have 98? Yeah. Okay. So shall we move to the next? According to Newton's second law, you know that, right? That is the Newton's second law applied to rotational motion. So I'll ask you, tell me what is the Newton's second law applied to rotational motion? Force become torque, mass become inertia, acceleration become angular acceleration. So this is the Newton's second law. We call the rotational dynamics. Dynamics is when you apply the Newton's second law. So normal motion, it is the usual Newton's second law. Net force is equal to mass into acceleration. For rotational dynamics, you replace things, right? Force is replaced by torque. Mass, or which we call the inertia, is replaced by rotational inertia, or another name is moment of inertia. And the acceleration is replaced by angular acceleration. So now you know the answer. So angular acceleration is directly proportional to the net torque. Angular acceleration is inversely proportional to the moment of inertia. So the answer. So it's saying directly, so the answer is. Now it's a rotational dynamics. Applying the Newton's second law for rotation, a ventilation fan, it's like a wheel, it is rotating. With a moment of inertia is given. So moment of inertia of the rotational point, which is at the center. So this is the I. As a net torque, so the net torque is given. What is alpha? So just a matter of substituting in the equation. Very easy, direct question, and everything in SI unit, substitute and get the answer. Number 32. Yeah, Newton's second law for rotational motion. Rotational motion. Newton's second law for regular linear translational motion is net force is equal to mass into acceleration. So, for rotational motion, we don't use force because force is not the right thing to use instead of, because you have to talk about how it is rotating. The tendency of the rotation of a force is represented by the torque of the force. So force is replaced by the torque, acceleration is replaced by angular acceleration, and the mass, which we call the inertia, the normal regular inertia, it is replaced by the rotational inertia. This is called the I. It is also called the moment of inertia. Same thing, two different names. Moment of inertia or rotational inertia. Okay. Question number 32. A uniform rod of mass 0.2 kilogram and length 1 meter is placed on a horizontal frictionless table as shown in the figure. The rod is pivoted at the center and the force is 12 Newton. And what is the angular acceleration? So it is just the same question, but here is without numbers, here with numbers. All you have to do is to substitute. So angular acceleration is the net torque divided by inertia. Right. Now again, you should put the point, right? The point is the center point. The pivot is at the center. So you have to take the net torque above the center divided by moment of inertia also above the center. The net torque, net mean the torque from all the forces, right? That is the sum of all the torques. But luckily for us, at the pivot point, there will be forces other than this applied force, but the torque from all the forces acting at the pivot point will be 0 because R is equal to 0. The only force we have to worry about is this force, the torque coming from this applied force. So this will be R, which is L over 2 multiplied by the force. So you don't even have to worry about the positive negative signs. Everything, there's only one force, the angular acceleration will be in the same direction as the torque. If you want, you can put the negative sign because it's negative, you can see it is negative. Divide by the moment of inertia is 1/12 ml squared. That's it. You substitute. And of course, you will say, I'll get a negative answer. Doesn't matter because, we are just interested in the magnitude only. Negative tells you the direction of the angular acceleration. Obviously, it is clockwise. That is why it is negative. So that's it. You just substitute and you should get this answer, 360. I finished it, but I can answer your questions, okay? If you have a question and if you want me to solve another, it is already 12 o'clock. We took a lot of time. Yeah. So I will stop